Here you go. 1, 2, 3, 4, and 5 from the exam in this first video. Okay, number 1. A circle is a set of all points equidistant from a given point. You don't have to say all. You can just say points. You can say distinct instead of given point. The important thing is set. Set. Equidistant. You don't even need to use this word. You could say a set of all points that are the same distance. So, but this is important. This, you could break that up into multiple English words, and that would be okay. You know, that's part of the definition, the line and the point here, directrix, focus, part of the definition. But to get full credit for these definitions for a circle and a parabola, you need this word in there, right? Because we have point, line, plane, set, number. These are what's called primitive notions, right? The most basic of ideas. And these are the undefined terms. Right? These, and they're undefined. Basically, it makes them like the building blocks of all other definitions. These are undefined terms so that we can have defined things like parabolas and circles and triangles and things like that. So it's kind of crucial to get this word in here. Just, you have a point, you have parabola, you have this word, line. Here you have points. So that's important. But this is too. These are the building blocks of what we're working with in math, these undefined terms and these axioms. So that needs to be in your definition to get full credit on these right here. So that's 1, 2, 3, 4, and 5. A straight edge and a compass. Let me focus the camera again, make sure it's focused. I should set this up so I can see how my camera is focused. Oh, okay. So, the midpoint. So we want a perpendicular bisector of this segment here. So something that goes through this, we're going to find the midpoint. Finding the midpoint. So here, mark the circle here on this side, and then not changing the compass at all. We make those marks. Now this line segment here, this goes through this perpendicular at the midpoint. So we know that this point right here at this intersection, this is in the set. That's in the set of all points equidistant from the focus and the directrix. All right, this is halfway, here to here. All right, so we can find that with compass and straight edge. This point is in the set. And we know that this is the vertex. Okay, now imagine how we might sketch this, more points with a compass and straight edge. Not so easily done. But we can imagine that, let's see, to find another point in the set, I definitely can't go up or down on this. on this line segment here, on this perpendicular. Because clearly this is the only point. This is the only point on this line segment that qualifies as being equidistant from here to here. It's the midpoint. So I'm going to have to go a little bit left or right. Got to go left or right to find the next point. Well, let's take an extreme left or right. Say I were to go out here. I'd put a point out there. No way. Look at this. The distance there, pretty short compared to this distance. No way can I just go out to the right. And I certainly can't go below, because that just puts me even closer to the line. So as I go this way to find points in the set of points equidistant here, it's going to make the shape of a parabola. And oops, that's not very good. Probably, who knows, something like that. We know it has to bend up, right? It's got to bend up to meet the definition. Okay, for a sketch, for an illustration, a graph with compass and straight edge, this one point, well, we can sketch that. So to get all of the points, to get more than just this one point in the set of all points equidistant from here to here, or from here and here, to get more than just this one point, we're going to need some coordinates. We're going to need to put this in a coordinate system. So we're kind of going from like Euclid in this like nowhere space, no origin, no anything, no axis. We're going to go from this Euclidean kind of nowhere plane to analytic geometry. So this right here is synthetic. And we're going to move this to find an infinite number, to find this set, this infinite set of points that belong in this parabola. Thank you, Descartes. We have analytic geometry. Analytic geometry. So the way we turn this into a solution in analytic geometry is to give this thing a location. Right? We need to put a coordinate system on this line, on this plane, for this line and these 2 points. So we don't have to know where the origin is. But we do want to name this something. This point is in the set, so we should start with this. We're going to give it a name. Okay, we're just going to label it. I'm going to call it HK. HK. And we're going to have this first coordinate be for an x-axis. In this second coordinate, this is an ordered pair. Ordered pair, a pair of numbers in a specific order. This is going to be wherever the x-axis is, down here. Let's imagine it running parallel to this line, because we're choosing our coordinate system. We started with this nowhere plane. Now we're just going to put a grid on here and figure out where things are. We're going to come up with an expression that's going to describe this infinite set of points. And so I need to start by locating this point that's somewhere in this Cartesian plane. It's in a Cartesian plane. So I'm going to call it HK. You can call it something else, but this solution is going to use these symbols, H and K. So from there, what else can we label? What else? Well, we certainly want to label a point, a random, an arbitrary point in this parabola. So say maybe a point out here. Just suppose you don't know where that is. We're not sure. It's a mystery point. It could be any point. We'll call it XY. Because this is truly what we're talking about here. This set of points. So here's our XY. Now we look here at our vertex, and we know that this distance from here to here is the same as this distance here to here. Well, let's call this length the focal length of the parabola. And let's say it is, well, let's give it a symbol. Let's call it P. That would make this line right here, y equals k minus p. Because here we have the vertex, hk, so its y-coordinate is k. And we're going to go straight down from this y-coordinate. Vertical axis movement along the vertical axis, or along a line parallel to the vertical axis. We're going to move a distance p to get to this line. So we can name this line y equals k minus p. So here we can label the focus. So the focus here, well, we got to choose whatever we want for this vertex. So we called it h, hk. So we made this x-coordinate h. Because we did that defines some other things for us. For example, on this line right here, everything is h. Right? This is going to intersect at a right angle, the x-axis. So this point here also has the same x-coordinate, h. This y-coordinate for the focus is a p distance higher for its for its y value. So it's k plus p. And so we chose this. We started here. The one point we know we have, we're going to label that. This is in the sketch. In our Euclidean space, our synthetic plane. Now we're in an analytic plane, the Cartesian plane. And we gave this a location, we put it on the map. Now, according to this map, where are these other things? So this is what we've set up. Now, from the definition of a parabola, we know some things. We know that the distance from this arbitrary random point here, xy, the distance from this to the focus, that right there, and then this distance, are the same. And this is a horrible sketch because this doesn't allow me to, well, it's good enough. Watch. I will in my sketch here, I'll just come across this way. Okay, and over here, I'll just magnify. This right here, we'll make it look like this. Not to scale, right? It's out of proportion here. So here's our XY. Right, and our focus. Okay, we're looking for the distance. This distance here compared to this distance here. I'm going to use a separate sheet of paper. Here's our focus. There's our point, XY. This is our focus, which is H and K plus P. So this distance here is X minus this X value. That's this leg. This is the point. We want this distance right here. That's what's in question. Okay. To find this distance, it's here. Actually, you know what? That's what erasers are for. That's why we do this in pencil. There we go. Not too much of a mess. So I'll put an imaginary point up there. So we're looking at this distance here. Okay, and to find that distance, we can make a triangle, a right triangle. Cartesian plane, easy to find right triangles. Sketches could be much better. Okay, but that's what we got. XY. So this right here, this is X minus H. This right here minus this. We travel from here to here. That's the length of this side of the triangle, X minus H. Okay. From here, we know that this point here has a Y value, K plus P. So Y minus K plus P. That's this leg of the right triangle. Y minus K plus P. This leg is X minus H. So we want to know this distance here. That distance. Well, Pythagorean theorem tells us that this squared plus this squared is equal to that squared. So this distance is the square root of this squared plus that squared. So we can find that. There's that square root. X minus H squared plus this quantity. Y minus K plus P squared Took the square root, so that means this distance. This distance is that. And we know that that distance from this point to the focus is the same as the distance from this point to the directrix, which is y equals k minus p. So here, this distance, this y value, minus this y value. So this is the setup to the definition, moving the definition of a parabola from synthetic geometry to analytic geometry. Right, what we did here was we put a coordinate system onto the plane. So at first, all we had was this, the vertex. We could find that with a compass and straight edge. And then we labeled that to a coordinate system. And we were able to map this. We'll just give that its random name. And now from the definition, we know that the distance here is the same as the distance here. And we have an expression for each distance algebraically in this coordinate system. So this is what's going to give us an infinite number of points in the set that is the parabola. A parabola is the set of points equidistant from a line and a given point. So this right here is an infinite number of points. We can do this algebraically. This is analytic geometry now. We've moved from synthetic geometry, a nowhere plane, to a Cartesian plane, a coordinate system. Analytic geometry is allowing us to write algebraic expressions to account for these infinite sets. Okay, here the equation is copied over. So this string of symbols is going to get longer before it gets shorter. And what I'm going to do first is I'm going to square both sides. And that's going to let me get rid of this radical here. What I'll do on this side right now is I'll just FOIL this with itself. Right? We're squaring, so this is going to give me y squared minus 2y times this quantity, k minus p, and then this squared. And on the right side, I'm just taking that radical off. So I'm going to be left with this right here, which I'm going to basically leave alone, plus p, and this thing is squared. Now, over here, I'll distribute this through here and take the parentheses off this by squaring. So this gives me y squared minus 2yk. Negative 2y times negative p is positive 2yp plus this thing squared. So plus k squared minus 2kp plus p squared. I'm going to sharpen my pencil here. So we're going to leave that x piece, we're going to leave that alone. And write x minus h squared. And we're going to square this thing. And we're going to FOIL with itself here. So we're going to have y squared minus 2y k plus p plus k plus p squared. Right? That's foiling with itself. Okay? Now over here, I want to write this x minus h quantity squared plus y squared. I'm going to distribute this. So this is going to be negative 2yk plus or minus 2yp. And then let's square this. Get rid of these parentheses. Plus k squared plus 2kp plus p squared. Over here, we'll just rewrite things. All right, there's nothing more to expand. That's 2kp plus p squared. So we don't have these parentheses off, but we don't really want them off. We'll leave that the way it is. And now we can see that these go away, kind of cancel each other out. We can add the opposites of these to both sides to turn them to 0. We can do the same with p squared. Let's write that and that. And then what we have, a negative 2yp and a positive 2yp. Those got to stay. Those aren't the same. A negative 2kp. We have a 2kp over here. We do, but it's positive 2kp, so those got to stay. A negative 2yk and negative 2yk. Those can go away. A k squared and the k squared, positive k squared. We can get rid of those. So we have a 2yp minus 2kp equal to x minus h squared minus 2yp plus 2kp. That's all that's left. This right here and this right here. Now from there, we can see that here we can factor out a 2p. We have y minus k. I'm pausing so that you can see for yourself what's going to happen before I write it. So we can take out a negative 2p here. Get y minus k. But we can just move those terms. We don't want to factor that. We have 4p now. This thing right here, we're going to add this to this side. We're going to bring this over here. Right? Algebra is just moving these things back and forth. So you can think of it as adding opposites and having the additive identities do the cleanup for you. Or you can think of it as moving the term from one side to the other, and then you just change its sign. So over here we would have well, we have this right here, 2p y minus k. And then this would be moving this over, turns it to positive, switches the sign, y minus k. Here we have x minus h, quantity squared. And this turns out to be 4p y minus k equals x minus h squared. Now, we multiply by the inverse of this to each side. So we're going to 4p y minus k equals that. And we're going to multiply by 1 over 4p. And there we go. Y minus k equals, oops, this is in the way of this line. I'm going to have to rewrite it. 1 over 4p x minus h squared. So we can move this k over. And this, you can call this a general form. Function friendly, y as a function of x, then you'll have it all by itself. And 1 over 4p, move that k over, plus k. Oops, I was writing off the... So that's the general equation for a parabola, the vertex form. This is the most friendly, I guess, form of the form, HK. So here we can see we're going to rewrite this on the next page, because we're doing 1 through 5. So let me get another piece of paper here. Okay, and let's see. Y equals, we have 1 over 4p x minus h squared plus k. Let's get this. That's what we're starting with here. Okay, so this is the general equation we found. So now let A equal 1 over 4p. So that y equals a squared, that quantity squared. So we're kind of massaging this to get it into the standard form, where it is in the nice little patterned order of polynomial. Okay, so we did that just by letting A be that. Okay, so now what we want to do to get the standard equation out of this, we need to do some expanding here. We need to get rid of these parentheses, so we're going to square this term. So here we have y is equal to a times what, x squared minus 2xh. I should say 2hx. I mean, it doesn't matter, they're the same, but this is the independent variable, right? So I like to have it as the rightmost symbol in this term. Put it on the right. Not required, just a preference. It helps my eyeballs. It helps for readability. and then we have h squared. That plus k. So let's get the a through here. So we have ax squared minus 2ahx plus a h squared plus k. So we got these parentheses off. We distributed this through. So now let b equal negative 2ah. And let c equal ah squared plus k. Most powerful word in mathematics, right here. Very powerful. Lets you do all kinds of stuff, right? Let. So now we let b be equal to this, c be equal to this, so that y now equals ax squared plus bx plus c. So there is now, we have our standard equation from the general equation. So y equals ax squared plus bx plus c. So if ax squared plus bx plus c equals 0, then I'm going to get another piece of paper. We'll just do this on another page. So if this, then what? Okay, what we're going to do now is we're going to solve. We're going to solve for x. We're basically going to find the roots for every possible parabola in the universe. Every parabola has this form here. The roots where it crosses the x-axis, and these could be anything, A, B, and C. First thing we want to do is we want to complete the square. We're going to derive the quadratic formula. So first thing we're going to do is we just want x's over here, x terms only. Just like that. Add negative c to both sides. And then what we want to do is we want to get rid of this a in front of the x squared term. We would like this coefficient to be 1. So we will multiply both sides by 1 over a. So over here we have x squared plus b over a, x equals negative c over a. Now what we want to do is we want to add 0. We want to add So now what we want to do is we want to half this and square it. So x squared plus b over a x, half of this is half of this coefficient and squared. So b over 2a, that's half of it, and we're going to square it. Now I can add as much as I want, whatever I want, to this side of the equation, as long as I do it to this side at the same time. Because I want to keep using this symbol right here. I have to do the same on both sides. Okay, so the reason I chose this was because I wanted a perfect square trinomial. A perfect square trinomial, because now I can write this side as x plus b over 2a squared. So this was strategically chosen so that I could then write this. Went from here, adding this quantity. And this is a choice, and this isn't. Have to add this. Why did I choose this? This choice was made. This is forced. This choice is made so I could write this. So write this trinomial as a square. And then over here we can write, we'll write b squared over 4a squared. Just take the parentheses off here. C over a. And then here we can say, well, this is b squared over 4a squared minus, multiply this by 1. This is just 1. Always multiply anything by 1. Not change the value of anything. Don't have to do that anywhere else. So that gives me 4a squared over here. 4ac on top on the numerator and a 4a squared as the denominator. Matches that. So over here I can write b squared minus 4ac all over 4a squared. That's equal to this. So then, from here, well, we want to solve for x. So we got to get it out of these parentheses. So we'll just square root each side. We have x plus b over 2a on this side. Over here, we have plus or minus, because this is something squared. Something squared, so this is plus or minus. And we'll square root this. So this is plus or minus this radical, b squared minus 4ac. And this is just becomes 2a. Bottom. Then x, I'm going to add the opposite of this. I'm going to add to both sides. And look, it already has the denominator. This is going to become b, negative b plus or minus square root b squared minus 4ac all over 2a. That's number 1 through 5. So here's our quadratic formula from the standard formula. We got from our general. We just said let a be this. So We could rewrite it. And then we just multiplied the a through. This right here is a, let's don't have any x terms. We made that c. So let c be this. Let b be this coefficient right here. So let b be this and c be that, so that we can write it like this: y equals ax squared plus bx plus c. So then if that's equal to 0, then some logic, some algebra, some multiplication, we get our quadratic formula.